Hi, welcome. So in continuation of my previous lecture, I said that subatomic particles can be grouped or classified based on whether or not they participate or whether or not they are affected by the strong force. So there are four forces out there in the universe. You have gravitational force, electromagnetic force, strong interaction and weak interaction, right? And based on whether these subatomic particles respond to the strong interaction, we can classify them into two categories: the lepton particles and the hadron particles. Leptons are those particles that are not affected by the strong interaction, that do not participate in the strong interaction. For example, electron, muon, tau particle and neutrinos. On the other hand, you have hadrons which experience the strong interaction. They do participate in any kind of a strong interaction. So I've talked extensively about leptons in my previous video. If you're interested in lepton particles, you should take a look at that video. In this video, I'm going to talk about the hadron particles. So hadron is a Greek word that means strong or heavy. So it is named as such because hadron particles, unlike the lepton particles, are not elementary particles. You see, leptons are elementary particles. That means they cannot be broken down into further smaller particles. But hadrons are not elementary in that sense. They are made up of further elementary particles, namely quarks. So hadrons are particles which are in a sense composite particles. So in the same way that atoms come together to create molecules, hadrons are those particles in which quarks come together to create hadron particles. They are not point mass particles, they are composite particles. They have a certain shape or volume or extension in space. In fact, hadrons make up the vast majority of ordinary matter. You see, normal ordinary matter that we know of, all the atoms out there, are made up of mostly three particles. Like you have a neutron and proton inside the nucleus, and you have the electron. Electrons belong to the lepton family, right? The neutron and the proton, they belong to the hadron family. So in a way, vast majority of the ordinary matter that we know in our universe is made up of hadrons. Now, to understand hadrons better, we can classify hadrons into two further categories. One is the category of mesons, the other is that of baryons. So mesons and baryons can be distinguished based on how many quarks they are made up of. You see, I said that hadrons are not elementary particles. They are made up of further elementary particles, namely quarks. So when quarks come together, they create these composite hadron particles. Mesons are those hadron particles which are made up of a quark-antiquark pair, while baryons are those hadron particles which are made up of three quarks. Now, further particles having more number of quarks has also been studied, for example, pentaquarks, etc. But we will not be talking about those particles today. In fact, vast majority of the hadron particles that are studied can be grouped into these two classifications, one consisting of a quark-antiquark pair, the other consisting of three quarks. These quarks are held together by the strong interaction. So the hadrons are a result of the strong interaction because the quarks interact with each other via the strong force. So it is because of the strong force that the quarks are held together to create these composite particles in the first place. And the strong force is in fact so strong that till now we have not been able to break apart these particles into individual quarks. We have not yet experimentally found free quarks. Quarks are always found inside a hadron particle along other quarks, together which they create these particles in the first place. Now, if we want to understand the distinction in the properties between these two classification of particles, we need to understand that most of the properties of these particles arise as a result of these quarks. See, mesons and baryons, their properties like electronic charge, spin, etc. arise as a result of these quarks. So if we understand how quarks combine to create certain properties, we will know the distinction between mesons and baryons. So let's look at a few examples, all right? So let's take the example of a proton and a neutron, and I will show you how their electronic charges are a result of the quarks. So you see, I have not talked too much about quarks. I will just talk enough which is necessary for the discussion. So there are, let's suppose, 6 kind of quarks or 6 flavors of quarks. You have up quark, down quark, top quark, bottom quark, strange quark, and charm quark. They have different properties, properties related to strangeness, properties related to electronic charge, etc. But for the sake of this particular discussion, let me tell you that quarks, as it turns out, have fractional electronic charges. So we know that, for example, an atom which is made up of an electron and a proton is neutral, right? And the electron has a negative electronic charge and the proton has a positive electronic charge. But the protons, which are nothing but hadrons, they belong to the baryon family, are made up of quarks, and these quarks have fractional charges. That means charges less than 1 electron. So the proton is made up of 2 up and 1 down quark, while the neutron is made up of 1 up and 2 down quark. It has nothing to do with the direction. These are just names. But as it turns out, the up quark has a charge of plus 2 by 3 electronic charge, while the down quark has minus 1 by 3 electronic charge. So what is going to be the total charge of a proton? So as it turns out, the proton has 2 up quark, right? So an up quark has plus 2 by 3 electronic charge. So since there are 2 up quarks, so plus 2 by 3 again. And 1 down quark which has an electronic charge of minus 1 by 3. So if you add these 3, it turns out that this comes out to be what? 3 upon 3, which is nothing but plus 1 electronic charge. So the proton, as it turns out, is positively charged by plus 1 E, where E is the electronic charge of an electron. On the other hand, if you do the same calculation for a neutron, neutron has 1 up quark and 2 down quarks. So the total charge of a neutron is plus 2 upon 3 electronic charge minus 1 upon 3 electronic charge minus 1 upon 3 electronic charge, which turns out to be how much? So they cancel out. You end up getting 0 electronic charge. That means the neutron is a neutral particle. It has no charge. So as you see, the electronic charge of hadron particles basically arise as a result of the summation of the electronic charges of the quarks that make them. So in a way, if you know the configuration of quarks which make up the different kinds of hadron particles, you can predict certain properties of those hadron particles. For example, another property is the property of spin, right? So as it turns out, the spin of a quark is half. So spin is basically a quantum number which is associated with the intrinsic angular momentum of elementary particles, known as spin angular momentum. And if you try to find the magnitude of spin angular momentum of these intrinsic particles with respect to some kind of external magnetic field, then the Z component turns out to be either plus h cross by 2 or minus h cross by 2. So associated with plus h cross by 2 is the plus half, and associated with the minus h cross by 2 is the minus half. So we can say that the spin of quarks is half. So based on this, we can get an idea whether or not the meson particles or baryon particles will be fermions or bosons, right? Since mesons consisting of 2 quarks, 1 quark, 1 anti-quark, so it can have configurations of spin up, spin up, spin up, spin down, or spin down, right? So which basically corresponds to a spin of plus 1, spin of 0, or spin of minus 1. So in a way, the meson particles, as it turns out, can have a spin of plus 1, 0, or minus 1. That means an integer multiple of the spin quantum number, which means that these particles are essentially what? Boson particles, right? So in a way, the meson particles turn out to be boson particles. They are bosons. Bosons means they follow the Bose-Einstein statistics, and they do not follow the Pauli's exclusion principle. The Pauli's exclusion principle says that particles which follow the Pauli's exclusion principle, no more than one same kind of particle can occupy the same quantum state. But bosons do not follow the Pauli's exclusion principle. That means more than one similar particle can occupy the same quantum state. So mesons are those hadron particles which turn out to be bosons. But on the other hand, if you look at, let's suppose, a baryon particle, all right, So baryon has 3 quarks, right? And each quark can have a spin quantum number of half. So what is the nature of configuration which is possible? So you can have all the quarks in the same spin. So you can have plus 3 by 2, or two of them oppositely aligned. Then you can have plus 1 by 2, or you can have minus 1 by 2, or you can have minus 3 by 2. So as opposed to mesons that can have spin of plus 1, 0, minus 1, the baryon particles can have a spin of plus 3 by 2, plus half, and minus 3 by 2. That means half integers. So the particles that have half integer spins, they are what kind of particles? They are fermions. So fermions are those particles that follow the Fermi-Dirac statistics. They follow the Pauli's exclusion principle. That means no more than one similar particle can occupy the same quantum state. So whenever you look at particles which are fermions and you look at their accumulation in different quantum states, you will always find that in one given quantum state you can have only one such similar particle. So this is one way in which we can distinguish mesons and baryons. So mesons are made up of a quark-antiquark pair. Baryons are made up of 3 quarks. The mesons are bosons and they follow the Bose-Einstein statistics. They do not follow the Pauli's exclusion principle. Baryons are fermions. They follow the Fermi-Dirac statistics. They follow the Pauli's exclusion principle. Also, there are other quantum properties which are also associated with quarks. I'm not going too much into detail because then that would be a different kind of a video. I'll talk about different quantum properties of quarks in maybe a separate video. I'm only discussing as much as is necessary for this particular discussion. All right, so now these are all quarks, right? I said there are 6 kind of quarks. You have up, down, strange, charm, top and bottom. But these quarks, they come together to create particles like hadrons based on something called a property called color. So it has nothing to do with the actual visual colors that we see. It is a quantum property which helps us understand how different kinds of quarks come together to create these composite particles. So let's look at a visualization. So color is a quantum property, all right. It has nothing, as I said, it has nothing to do with the actual visual color. It's a quantum property based on which quarks come together to create these composite particles like mesons and baryons. So how these quarks come together? The quarks, they interact via the strong force. The strong force is also sometimes known as the color force, because the way these quarks come together is that they try to create composite particles which are colorless. So there are 3 kinds of color, all right. So you have blue, red and green. So you can think of this as the analogy with primary colors. So when we talk about visual colors, we talk about primary colors like red, blue and green. And when primary colors come together, you create white. Now the quarks has nothing absolutely to do with the actual visual colors. It is just a naming convention to help us understand what is happening. So in the same way, for example, charge particles come together. So you have a positive charge, negative charge, which come together, they attract, they come together to create, let's suppose, an atom. Here in hadrons, these quarks, in the same way that in case of electromagnetic force, you have positive and negative charge. In the case of quarks, you have color, blue, anti-blue, red, anti-red and green, anti-green. All right, and the way they come together is, one configuration is where red, blue and green come together to create a colorless or a white, you can think of, baryon particle. So all the baryon particles consist of 3 quarks that are distinct from each other, apart from them being up quark or down quark or bottom top, whatever other, that is the property of flavor. Apart from being distinct in terms of its flavor, they are essentially distinct in terms of their color. So all baryons are essentially made up of quarks that are red, blue and green. And the other possibility is a meson particle where one color and its anti-color can come together to create a white or a colorless meson particle. So for example, you may have a red and an anti-red quark coming together to create a meson particle. I hope that is clear, because that is all I'm going to talk about in this particular case. So essentially, mesons are created by quark antiquarks that have a color and its anti-color, and these colors may be red, green and blue, while baryons are made up of red, blue and green. Now There are other quantum properties also, properties of strangeness, baryon quantum number, etc., etc. But I'm not going to talk about those properties in this video. I'll make another video where I'll talk about lepton number and baryon number and strangeness number conservation. I'll talk about those quantum numbers in that particular video. Essentially, what I want to say here is that these mesons and baryons, which are made up of quarks, arise as a result of quarks coming together to create these composite particles, and the properties of these composite particles can be understood by looking at how the quarks come together in the first place. Now, there are a large number of these kind of subatomic hadron particles in nature. So up till now there are around 140 meson particles that has been studied and around 120 baryon particles that has been studied. So 140 types of mesons and 120 types of baryon particles has been studied. However, vast majority of these particles are not seen in ordinary matter. So ordinary matter is consisting of neutrons and protons, which are essentially baryons. The vast majority of these particles arise as a result of high energetic reactions or particle decay. So for example, when cosmic rays enters the Earth's atmosphere, you may see lots of different kinds of subatomic particles arising in those reactions. You may see these kind of particles being created for a very small period of time in particle accelerators when particle collisions are taking place. So let me give you a little bit of a feel of what these particles are by discussing some very commonly known mesons and commonly known baryon particles. So there are many hundreds of these kind of subatomic particles that arise for a very short period of time in different kinds of decay processes or high energetic nuclear reactions, and it's not necessary for us to study all of them, but just for the sake of familiarity, I can demonstrate the properties of, or I can show the properties of few of the commonly known particles. So let's first talk about mesons. All right, so mesons, as I said, are made up of a quark anti-quark pair which has the properties of a color anti-color. They have spin of 0 and 1, so integral spin. They are bosons, and mesons are particles which are not found in ordinary matter, in the sense that free mesons are not found. One of the commonly known meson particles is a pi meson. So you must have heard of pi meson while studying nuclear forces. So one of the first common theories of the existence of nuclear force and how nuclear force acts inside a nucleus was given by Hideki Yukawa and his meson theory of nuclear forces. You must have heard of it. So what Hideki Yukawa, who was a scientist who gave one of the first successful explanations about the nature of nuclear force, said was that inside the nucleus you have a neutron proton, right? And these neutrons and protons are glued to each other to create the nucleus in the first place because of the strong force. And the way the strong force acts is that a neutron and a proton, or a neutron and a neutron, or a proton and a proton, they continuously exchange a particle within them, and this particle is what is known as the pi meson. So a neutron and a proton, they are continuously exchanging pi mesons in between them, which is creating the effect of a force that is holding these particles together to create the nucleus in the first place. So these pi mesons are essentially mediators or force carriers that, when they are exchanged continuously between neutrons and protons, lead to the effect of the nuclear force holding the nucleus together. So usually these pi mesons, the lightest of all the mesons out there, they don't exist freely, but rather they exist as mediators inside a nuclear configuration. So these pi mesons are also sometimes known as pions. They are the lightest of all mesons out there, and also the most commonly known. So just to give you a little bit of a taste of what these particles are. So one of the commonly known mesons are the pions. So you can have pi minus, pi naught, pi plus. Okay, so this superscript basically tells us about the charge. So pi minus has a negative electronic charge. pi plus has a positive electronic charge and pi 0 has a 0 electronic charge. The pi minus and the pi positive are essentially antiparticles of each other. So the antiparticle of pi minus is pi plus, all right, and pi naught is an antiparticle of itself. They have 0 spin, all right, so they are bosons, and the quark configurations are written here. So the pi minus is made up of an up and an anti-down quark. The pi plus is made up of a down and an anti-up quark, while the pi naught can be an up anti-up quark or a down anti-down quark. There are different kinds of decay modes associated with the pions. So pions are found within the nuclear configuration, but if they are free, then they will immediately decay into further other particles. So a positive pion can decay into an anti-muon and a muon neutrino, while a negative pion can decay into a muon particle and an anti-muon neutrino. So the muons and the neutrinos are nothing but lepton particles. So essentially what happens is that a pion particle decays whenever it is free immediately to these lepton configurations. On the other hand, the neutral pion can decay into 2 gamma photons. So these are some of the decay branches associated with pions. Whenever they are found free, they immediately decay into these kinds of either gamma photons or these lepton particles. There are other meson particles also. Some very commonly known of them are the eta particles and the kaon particles. So eta particles, you can have eta as well as eta prime. The kaon particles, you can have k plus k minus k naught again. So k plus k minus k naught, here the plus minus naught represents the electronic charge, either plus 1 electronic charge, minus 1 electronic charge, or 0 electronic charge. And I have written the quark configurations also here. The eta particles are made up of a combination of up, down and strange quarks. I have written the decay mode for the eta particles also here. So eta particles are usually created between collisions of pions with nucleons, while kaon particles are usually created whenever cosmic rays are entering the Earth's atmosphere, and it leads to the creation of various particles, and kaons are one of them. So the history of particle physics is associated with the discovery of different kinds of particles in different kinds of reactions while studying cosmic ray interactions, while studying the decays of high energetic particle accelerator reactions. And it's not possible to study all the particles, at least not for the sake of our discussion, but just for the sake of an introduction, pions, eta particles, kaons are some of the commonly known mesons that can be created in certain scenarios. So next, go ahead and look at some commonly known baryon particles. So just like mesons, there are hundreds of baryon particles out there. It might get quite confusing when you try to look at different kinds of these hadron particles, because so many of them are out there. But there are 2 very common baryon particles. For example, the neutron and the proton, right? Ordinary matter is made up of electron, proton and neutron inside the atom. Electrons are leptons, neutrons and protons are hadrons, and especially they fall under the category of baryon particles. So the most commonly known baryon particles are the neutron and the proton. So as I just now said, proton is made up of 2 up and 1 down quark. Neutron is made up of 1 up and 2 down quark. Their electronic charge of +1 and 0 arise as a result of the fractional charges of these quarks involved. Also, the spin of the neutrons and protons, as you probably already know, are spin half. So they are fermion particles. Now, out of all the hadrons out there, so you see most of these particles that I'm showing, they arise as a result of some sort of a high energetic nuclear reaction. The most stable out of all these hadron particles is the proton. So as it turns out, there is speculation that the proton probably has a mean lifetime of somewhere around lifetime which is even greater than the current lifespan of the universe. So the proton is in fact a very stable hadron particle. It does not decay further into other particles. However, the other hadron particles, mesons as well as baryon particles, they will, the moment they are formed, in a very short period of time undergo decay to further particles. Even the neutron, you see, neutrons are stable as long as they are part of a nucleus. So inside the nucleus the neutrons exist, but the moment you have a free neutron, the free neutron will immediately decay into a proton and lead to the emission of an electron and an electron antineutrino. The mean lifetime of this kind of a decay process is somewhere around 14 to 15 minutes. So even though neutrons do exist inside a nucleus, free neutrons are unstable and they decay within a few minutes of 14 to 15 minutes to a proton and an electron antineutrino. There are other particles also, other baryon particles, like for example lambda particle. So it's an electrically neutral particle. It has a few decay branches where it decays either into a proton or a neutron, and also emitting a pion in the process. You can have sigma particles, sigma plus, sigma 0, sigma minus. So plus 0, minus, they signify the charges, plus 1, 0 and minus 1. I have shown here the quark makeup also. It is made up of UUS, so S represents the strange quark, UDS and DDS, where D represents the down and U represents the up quark. These are some of the decay branches of the sigma particles. They also decay into either, so sigma plus decays into a proton, sigma naught decays into a lambda particle, sigma minus decays into a neutron. So these are some decay branches of the sigma particle. You have Xi particle. So the makeup of Xi particle is up strange and D strange, so down strange. So Xi naught and Psi minus, so they have a charge of 0 and minus 1 electronic charge. You have omega particle. So as you keep on studying these particles, you get more and more heavier particles which arise for a very fraction of a second during these kind of high energy nuclear reactions. So for example, when you have an omega particle, which is made up of 3 strange quarks, it's a very heavy particle and it decays immediately into a Xi particle and leads to the emission of a negative pion. This Xi particle immediately decays into a lambda particle and leads to the emission of a neutral pion, and the lambda particle immediately decays into a proton. So whenever these kind of heavier particles are formed in some kind of a nuclear reaction, then they will in certain period of time follow certain decay branches and most of the time lead to the most stable particle out here, which is that of a proton. So the moment a proton is reached, this kind of a decay branch stops. So the proton is a very stable particle out of all these hadron particles. The rest can be formed for a very small fraction of a second in different kinds of high energetic nuclear reactions. So I guess that is all as far as hadrons are concerned. I have tried to give you an idea of what hadrons are. These are particles that do experience a strong interaction. They are made up of further elementary particles called quarks. They can be further categorized into mesons and baryons. Mesons are made up of quark-antiquark pair. Baryons are made up of 3 quarks. Their properties are distinct based on how these quarks come together. So in the case of mesons, the quark come together to create a 0 plus 1 spin. So it's an integral spin. So they are bosons. In the case of baryons, the quarks come together to create plus half or plus 3 by 2, which is a half integer. So they are fermions. These quarks also come together based on what color they have, and they also lead to the different kinds of electronic charges, all right, as I have showed for the case of protons and neutrons. Now when you study elementary particles, you see different kinds of decay processes, different kinds of nuclear reactions, and it becomes very, very difficult to understand why certain kinds of nuclear processes are happening, why certain kinds of decay processes are happening, and which of them are allowed, which of them are not allowed. So to understand how certain kinds of nuclear decay processes are possible and why some of them are not possible, we need to understand certain conservation rules. Okay, so conservation, apart from conservation of energy, momentum, the usual, there are certain other conservation laws that need to be maintained as far as elementary particles are concerned. So for example, conservation associated with what is known as lepton number or baryon number or strangeness number. So I will talk about these numbers and these quantum numbers and how these quantum numbers play a very important role in their conservation in certain decay processes, thereby giving us a certain kind of a clue as to what kinds of decay processes are possible, are allowed, and what kind of decay processes are not possible and not allowed, because sometimes it becomes completely kind of a cumbersome or chaotic to see all these different kinds of decay processes happening. So in the next video, I'm going to talk about these quantum numbers and how these quantum numbers give us a better clarity as to what sort of decay processes are possible and what sort of decay processes are not possible. So till then, that's it for today. Thank you very much.